we're talking about biomolecules, and basically what that means is we're talking about proteins, carbohydrates, nucleic acids, and lipids. And you can't have a discussion on this without thinking of nutrition. And so I want to share you a story as we start. So my wife and I, we led a young couples small group at a church that we lived at in Ohio. We didn't live at the church, we lived in Ohio and went to this church. But, sorry, the grammar was a little weird. We had this, one of the wives, she would like get on a kick and she would lose like 40 pounds. And then she would like slowly gain the weight back, and then she'd get on a kick again, she'd lose like 40 pounds. And what she did was she just did like 0 carbohydrates, like absolutely 0. Not like a low carb diet, like a 0 carb diet. It was impressive. But so one time she was on one of these kicks and they invited everybody in the small group over to their house. And so we show up to the house and there are cinnamon rolls strewn across the front yard, all over the place. And I'm like, wow, this is really strange. I don't know what's happening here, but this is kind of interesting. I don't know if like this is how they run their house parties. And so we knock on the door, nobody comes and answers. And I was like, wow, this is really weird. My wife and I are usually the first people to show up because that was expected of us leading the class. So we just kind of waited a while, and then finally husband opened the door and you could hear his wife crying. And I'm like, man, now this is really weird. Like, do we need to cancel? He's like, no, it'll be fine. He's like, what happened was I forgot she was on one of these kicks, and I made these cinnamon rolls for everybody to come and experience in them, and she couldn't handle the smell, and she snapped. And she grabbed the cinnamon rolls and threw them out the front door and then felt so embarrassed by it that she started to weep. But he's like, I'm counseling her, we're working it out. We'll be fine. So then my wife and I went and cleaned up the cinnamon rolls. I kept those that weren't too messed up and I took them home with me, put them right into my car, and then she didn't have to worry about them, and I didn't have to worry about where I was going to find breakfast for the next 3 or 4 days. It was wonderful. So I thought I'd share that with you. It's one of my fondest memories of the entire time I lived in Ohio, really. All right. So for this chapter, we've got, I think it's still 4, it's 5. Wow, 5 questions that we're going to deal with. The first one we'll deal with pretty quickly. So we talked last time about why do elements behave certain ways, and why do elements behave certain ways?
Because of valence.
Because they have a certain number of valence electrons. They want 8, and they're going to do what's necessary to get 8. But molecules are formed by elements that have already done that. They've formed a molecule to accomplish that very feat of having 8 valence electrons. And so then we need to talk a little bit, okay, well, why do molecules behave the way that they do? And it'll be fun. You'll enjoy that. Then we'll talk about all of our 4 different types of biomolecules. Why are carbohydrates important for life? How are lipids used by living organisms? Why are proteins so important? And how do nucleic acids store information and energy? And, yeah, that last one's a good one. Okay, so this one we're going to move relatively quickly through slides, but not really through information. So don't get... Yeah, I hope you don't get overwhelmed. There are a lot of slides, but it's okay. We'll be fine. You'll be fine. I'll be fine. So how do they behave? Okay, first we need to talk about what organic molecules are. So organic molecules are any molecule made up of a carbon backbone. If it's made up of a carbon backbone, it's an organic molecule. It doesn't matter what else is there. If it's got a carbon backbone or a carbon skeleton, skeleton's probably a better term. You'll see why that is in a minute, because backbone, you're like, backbones are straight unless you have scoliosis, right? Backbones are straight. But some of these are like rings, and you're like, that doesn't look like a backbone at all. So skeleton's probably a better term. Anyways. So anything that's made up with a carbon skeleton is a complex, or is an organic molecule. It doesn't have to be complex. And then many of these are called hydrocarbons. And what that means is they contain almost exclusively carbon and hydrogen. Carbon and hydrogen. Okay? And sometimes these can be millions of atoms large. Millions of atoms large. Almost exclusively carbon and hydrogen. So let's go back over here. Look at this periodic table. We know that carbon wants 8 valence electrons. we know that it has 4, right? So it's got to share 4 more electrons. Really has to share all 8 electrons with either one other atom or a series of atoms to make this happen. Most of the times it's a series of atoms, which makes carbon such a wonderful skeleton building atom, right? So carbon, we know it's going to struggle to get 4 new electrons. It's just, that's really difficult for it. Because to find 4 is hard, but also carbon is not very good at pulling electrons away from the atom or the nucleus of another atom. Okay? It's not very good at it. Oxygen, great at it. Carbon, not very good at all. Carbon and hydrogen are about the same. Their desire or their ability to pull an electron away from the nucleus of another atom is about the same. Meaning, when they share electrons, they share them very evenly. Which is like the sharing that happens between identical twins, I presume. Okay? It's not like the sharing that happens between other siblings, right? The sharing with other siblings is never even, right? So whichever the dominant sibling is, that's what gets more, right? I have a brother that's 2 years younger than I. That wasn't enough to make it to where I got the dominant share. I outweigh my brother by 100 pounds. So my brother is very scrawny. Actually, he's kind of thickened up a little bit now. He looks normal. But as a kid, he was very scrawny and gangly. He looked like Abraham Lincoln, right? If you've never seen a picture of Abraham Lincoln, go find one. Just very gangly. And so everything my brother and I shared, we shared. Basically, when I didn't want to play with it, he could use it, right? That was how we shared. We shared a room. It was basically he had a bed and everything else belonged to me. Even his bed belonged to me, but out of grace, he was able to sleep in his bed, right? So carbon and hydrogen, they share electrons very evenly, okay? So what that means is they're very, very boring, because what determines how an atom is going to behave is its desire and how it's going to get 8 valence electrons. What determines how a molecule is going to behave is how the electrons are distributed in the molecule. Okay? So if you just have carbons and hydrogens, they're very boring because the electrons are basically distributed evenly. Carbon doesn't have any desire to do something other than bond with hydrogen because it's already sharing evenly. Hydrogen doesn't have any desire to do something that other than bond with carbon because, again, it's sharing evenly. It's a great relationship. But when we start adding functional groups, now we do something very interesting. Can you read that with the trees in the background? Okay. Sorry, I like the trees, but I realize it does create some issues. When we start adding functional groups to these hydrocarbons, we do something more interesting because we force the carbons to share electrons with something that isn't hydrogen. To share electrons maybe with oxygen, or with sulfur, or with something else, nitrogen, that are much better at pulling electrons away from something. And then carbon gets itself into an uneven sharing relationship, okay, when we start adding these functional groups. And so our complex organic molecules, or our biomolecules, our carbohydrates, our lipids, our proteins, and our nucleic acids, they are hydrocarbons with functional groups added onto them. And so now we can predict the way a molecule is going to behave by what functional groups it possesses. Okay? And again, I want you to remember that it's all based on how the electrons are being shared. If you have a molecule so that carbon has technically got itself 8 valence electrons, okay? So let's say we've got this carbon right now, it has 4. Okay, it has 4 valence electrons. What about hydrogen? How many does hydrogen have? 1. So if carbon forms 4 bonds with each of 4 different hydrogen atoms, now carbon is sharing the 1 from each of those and sharing the 4 that it already had, and so now it's got 8, right? That makes sense? And it's an even sharing. Okay, they're sharing those 8 electrons evenly. But let's say we add a functional group on here, and now carbon is sharing some electrons with oxygen. And so let's say 4 of the electrons carbon is sharing, it's sharing with 2 different oxygens, or even 1 oxygen, but they're sharing 4 electrons. Oxygen is much hungrier for electrons than carbon is, and it's much better at pulling those away. Oxygen's the older brother. Oxygen is me. Carbon is my brother. And listen, my brother turns 30 years old this year, and he still is afraid to bring things around me thinking that I'm going to take it away from him. It's awesome. It's so cute. I'm like, dude, you're 30 years old. I'm not going to take your stuff away from you. Unless, of course, I want it. Then, yeah, we'll take it. So if that carbon is sharing those 4 electrons, that carbon will do things to change that bond to something different so that it can share the electrons more freely. Okay? Make sense? Okay, cool. So let's see these functional groups. This is a diagram right out of your text. Listen, I don't need you to know how these are going to behave. If you want to, that's wonderful. I just need you to be able to recognize these. Recognize them and name them. And so I'm going to draw them bigger because they're a little bit small on here. This R represents some hydrocarbon. Okay? So R, wow, that is really effective. Oh! Man, I didn't call bank though. I didn't call bank, it doesn't count. It doesn't count. And I don't have another. Is there another one? Oh, what is this? Can you even use this on this board? Oh. So R is some hydrocarbon. Okay, and when you see hydrocarbon, you know, wow, this is really boring chemistry because they're sharing really evenly, right? They're identical twins. They don't need anyone else. Have you ever seen the marriage? Are any of you an identical twin? You ever seen like what percentage of identical twins get married compared to the normal population? It's way, way lower. And you're like, well, that kind of makes sense because they share everything so evenly, they don't need anyone else, right? Sorry. Anyways. You know, I have to tell you this. So I went to graduate school at a place that only had 3 full-time faculty members. They had 3 full-time faculty members in the entire department. 2 of them were identical twins. Like, what's the probability of that? I mean, they weren't twins with each other. Both their twins did something else. But they were identical twins. And I'm like, man, that's so weird. And sometimes they would switch it up just to mess with us. And I'm like, it never gets old. Like, I had friends that were identical twins in high school, and they enjoyed doing that. These guys were in their 50s and still enjoyed, like, playing the switcheroo on their sleep. Can they figure it out? Okay, so R is a hydrocarbon. Okay, so anytime you see R, you're just going to see hydrocarbon. We don't care about that because it's boring chemically. But when we've got an R attached to an OH, okay, this group right here, this is a hydroxyl group. Okay, you need to be able to recognize that. I don't need you to know how it's going to react, but you just recognize that's a hydroxyl group. Okay, and then if this O is attached to a hydrocarbon, you know that O's dominating those electrons, right? And then we've got R doubly attached to an oxygen. Let's get the carbon in there. Sorry. So we've got R attached to a carbon. This carbon is doubly bonded to an oxygen and bonded to an H. And we call this a carbonyl group. Okay, a carbonyl group. And again, if carbon is sharing oxygen or electrons with this oxygen, you know that's not an even sharing, right? So this carbon's going to want to change this bond to a hydrogen or to another carbon. Okay, and then there's another type of carbonyl. The carbonyl is basically this right here, this carbon-carbon double bond. So it doesn't matter if this is an H or if this is some other hydrocarbon, it's still carbonyl. All right. Any questions? Yeah, Tara.
So you said you want us to memorize these in the functional groups?
Yes, just the functional groups. Yeah, I just want you to be able to recognize them. I'm not going to, so I won't give you like a, because you might be thinking, okay, well, how's this going to show up, right? What is this going to look like on a test? I won't give you like functional groups and then make you match them to the names. I won't do that. I might do that on a quiz because you have your book with you, but I won't do that on an exam. But on an exam, I might ask a question of, why does this molecule type behave this way? And you're just like, well, I don't know. It must be because it has this functional group, because we know the hydrocarbon's boring, so it must be because of the functional group. And again, there you don't need to know exactly how the functional, you don't need to memorize how this functional group behaves, but you know that, oh, it has this functional group, this is what it's called, and so that must explain the chemistry.
Okay, so just to clarify, you don't need to know like alcohols and then aldehydes versus...
Oh, no. Not for this class. For organic chemistry, absolutely. Why is the air conditioning on in here? I mean, it feels great, I love it, but it's a little surprising. Is it? So here we have an R attached to a carbon, and this carbon is doubly bonded to one oxygen and singly bonded to another. This carbon is very unhappy, right? This is a brother with 3 older brothers, right? Man, that'd be rough. And so this right here is a carboxyl functional group. And then I'm going to give you one more. The other two I'll show you, but they're easy to recognize because they have things that don't really occur in others. So here's an R that's bonded to an NH2. And this is called an amino group. And this one, actually these two are going to be the most common that we're going to interact with in this course. And you find them both on the same type of molecule. And then you're like, wow, this is going to be a very, very reactive molecule because it's got 2 functional groups on it. And it is. But anyways, we'll get to there in a minute. All right? So are there any questions about these? And again, I just need you to be able to recognize them. So if you infer that as you need to memorize it, that's fine. You can memorize these. But you just know like you won't be assessed on your ability to recognize it. The next one is a phosphate group. We'll see this a lot, and it's got a P in it. And P stands for phosphorus, and it's a phosphate group. And then this sulfhydryl group has a sulfur in it. So those are very unique. We see this sometimes in this class. We'll see this relatively often, but only in one molecule type. Only in one molecule type. All right? Okay. I think we should do it. We're going to do it. We're going to take ourselves a lecture break. And so what I want you to do is this. I want you to work with those around you, take about a minute, and I want you to draw a hydrocarbon that has this functional group. I want you to draw a hydrocarbon that has this functional group. So instead of the R, put some hydrocarbons, put in a hydrocarbon, some carbons and some hydrogens, and just to get some experience drawing these molecules. Okay? And just do these 2. I mean, if you want, you can add the other 4 functional groups as well. But I want you to just take about a minute working with those around you, and I want you to replace this R with a hydrocarbon because I want you to visually see which carbons are going to be most interesting. Which carbons are going to be most interesting. Okay? So take about a minute. Draw a couple of those if you want to do it by yourself, because that's fine. You can draw it by yourself. Okay? 1 minute, starting now. Yeah. We're not going to get through all of chapter 3.
So what about on this part? Great. So, yeah. And then, yeah, that one. Then you have that hydrogen. Right. Yeah, you're right.
All right. It's been about a minute. If you haven't drawn them yet, it's okay. We'll do it together. Sorry, I can't wait longer than a minute because I don't know what to do while I stand up here. I mean, if it was just a matter of like not knowing what to do with my hands, I'd just put them in my pockets. I just don't know what to do with all this energy inside of me other than talk to you and write some stuff on the board. Okay, so we'll do a hydroxyl group. So I'm gonna make this relatively simple. I'm just gonna put 4 carbons. I mean, if you want, I told you these could be hundreds of millions of atoms long. If you want to draw 100 million carbons, go for it. That would take a long time. Okay, so here we've got this. Now, we know carbon's going to form 4 bonds, right? Right? That's what makes it such a great molecule to build the skeleton of an organic molecule, because it needs to make 4 bonds to be able to share. Every bond represents 2 shared electrons, and so it's got to make 4 bonds to have 8 electrons around it. Okay? And so right now this carbon is making 2, so it's going to make 2 more, and we replace the R with what? A hydrocarbon. And a hydrocarbon has only carbon and what else? Hydrogen. Man, it's so wonderful when the name means something. Because a lot of the times, this class isn't as bad, but a lot of times in biology, things are named after people, and they don't mean anything other than who found it. Like, why do I care about that? It was like 400 years ago. He literally has no relatives alive that even care that he's still getting credit for it. Why can't we just name it something that makes sense? It's a wonderful question. Okay, so here's a hydrocarbon. Okay, it's a hydrocarbon with a hydroxyl group on it. Of all of these carbons here, which is the most interesting chemically? This one here. And why? Because it's bound to something that it cannot share electrons evenly with. So this carbon would love to have bonds with something else. Like right now it technically has 8 electrons, but really 2 of those are hanging out almost exclusively with oxygen. Right? It's like when your little brother comes to school with you and technically your friends are his friends. They don't really care about it. I mean, I care about him because he's my brother, but like my friends do. Gosh, you guys are going to think we have a terrible... My brother and I actually have a great relationship, despite all of the horrible things I did to him as children. Okay, so we've done a hydroxyl group, and now we need to do the carbonyl group. We'll still do 4 carbons, because I don't want to draw any more than that. Okay? And this R group, it's a hydrocarbon, so it contains only carbon and what else? Hydrogen. Right now this carbon has 2 bonds, so we need to add 2 more hydrogen. This carbon has 2 bonds, we got to add 2 more hydrogen. This carbon only has 1 bond, so we got to add 3 more hydrogen. This portion of it, very, very boring. Very little chemistry. This carbon is a little bit more interesting. Now not only is it sharing 2 electrons with this thing that's an electron hog, but it's sharing how many? 4 electrons. Each bond represents 2. Yes? Now it's sharing 4 electrons with this electron hog. Now this carbon's going to be very, very interested in switching up its current situation. Okay? Even more so with this one. So these are very reactive. Formaldehyde has this functional group. You know what formaldehyde is? It's what you use to preserve tissue. Yeah, very reactive. That's why you don't drink it. I mean, it's carcinogenic. It actually mutates your DNA, and that's why we don't use formaldehyde anymore in labs. They use other things, because formaldehyde is super reactive. It mutates your DNA, causes cancer. All right, any questions? This is something that's helpful to be able to do. All right, a couple more things about biomolecules, and then we'll start talking about our specific types of biomolecules. So you have to know, for every organic molecule we have, almost every organic molecule we have, it comes in 2 different forms that are mirror images of each other. Whenever you have a carbon that's bound to 4 different things, you have basically 2 ways those can be oriented. Neither of these carbons they're both bound to hydrogen. This one's having 2 bonds with an oxygen. But for a lot of these organic molecules, when we have a carbon that's bound to 4 different things, you have 2 ways those can be oriented. And they're mirror images of each other. You call them the left version and the right version. And whenever you carry out a chemical reaction, you produce both, and half of them are the left version, half of them are the right. But living organisms only recognize one of the 2 mirror images. And so this is really, really interesting to be able to explain how this actually came to be, where enzymes only recognize one of those 2 mirror images when both exist. We'll talk more about this, I don't know, in a couple of weeks. But anyways, this is just kind of like a foreshadowing, a little sneak peek of what's to come. You're like, man, I can't wait. Glued to my chair. And only because if I get up now, people will think I'm rude, right? Oh man, I'm hilarious. All right. So we can take almost any organic molecule and we can string them together. As long as they have some functional group with some reasonable chemistry, we can string them together, linking them together. It's called polymerizing them. And we do this using a reaction called a dehydration or a condensation reaction. And what it is it's a reaction that has water as a product. And so if we look at, say, this functional group here, where this carbon would really like to break its bonds with this oxygen, right? Make sense? When it does, we free up an oxygen that can be used for something else to actually free up some hydrogen, and we end up forming water as a product when we polymerize these. Okay? So when you look at these, you're going to be able to predict what's going to fall off because you're going to remember water is a product. And so I need to figure out some way to account for one oxygen and how many hydrogen? And two hydrogen, H2O, right? Or dihydrogen monoxide, if you will. So that we can break down those polymers, so we can string them together, but then we can break them down by doing the exact opposite, by doing what's called a hydrolysis reaction. Do you know what this root lysis means? It means to break or to cut. What about this root hydro? Water. And so this literally means to cut with water. And now water is a reactant, and you're basically doing the exact opposite. You're using water to cut these bonds versus forming the bonds which releases water. And you're like, wow, that's so awesome. No wonder bread falls apart when I put it on my tongue, right? Or especially cotton candy, right? That's just a polymer of a whole bunch of sugars. Have you ever made cotton candy? You just put sugar in like that little thing and it spins it around. It polymerizes the sugar, which is why you get those, strands, looks like a cloud. You put that in your mouth and the water in your mouth starts hydrolyzing those bonds, cutting them up. You're like, where'd all the cotton candy go? And then you're bouncing off the walls and it's fine. All right. So here's a dehydration or a condensation reaction. We can see water is a product. Okay, here's the arrow showing the reaction, and here's water as a product. And what happened during this reaction? We took these three individual organic molecules and we strung them together, right? And you can see what is lost, the OH group from this one and a hydrogen from here to account for the one oxygen and the two hydrogen you need to make a water molecule. Same thing happened over here. Dehydration or condensation reaction to give us our other water molecule. And this is so wonderful. I mean, it really is wonderful. You may not see that yet, but you will. And then, so here's the exact opposite reaction. So now the arrow is here, showing the reaction has happened. Now water is on the other side, acting as a reactant, not a product. And now we're cutting with water. We're doing a hydrolysis reaction. And so you should predict we're going to do what with these bonds? We're going to break them. And here's these bonds breaking. And these are sugars, by the way. It's sugars and then linking them together. You're like, why would our bodies link sugars together? It's a wonderful question, which we'll talk about in the very next slide. All right, any questions about this? Man, I thought we were going to go through that first question. I was like, oh, we have 5 instead of 4, but we're going to go through the first one really quickly. 35 minutes later, we finished question 1. You didn't even know 35 minutes had passed, right? You're like, Dr. Ingo, it feels like 7 tops. My wife was asking me the other day, she's like, can you believe our oldest kid is going to be 8? I said, no, I can't. It feels like she should be 14. And then that was not what my wife meant. But she's like, can you believe she's going to be 8 years old? She's like, man, it's gone by so fast. I'm like, man, it has not gone by so fast. I don't even remember what life was like before I had her. She's so much like me. So it's like 2 of us, but she's a 7-year-old girl version of me. It's fun. You guys should meet her. How many of you have met her? Have any of you met my daughter? Gosh, she's a talker. I mean, who knew, right? A 7-year-old version of me. All right. Question number 2 of 5. We have 20 minutes to get through 4 questions. Why are carbs important? Why are carbs important? So, real quickly, I'll give this to you. Carbohydrates contain only carbon, hydrogen, and oxygen. So they have either this functional group or this functional group, or maybe the carboxyl group that is no longer written up there. But you're not going to find an amino group because that has nitrogen, right? Right? Do you remember that yet? You're not going to find a phosphate group because what does that have? Phosphorus. And you're not going to find a sulfhydryl group because that has sulfur. They only have carbon, hydrogen, and oxygen. And every single carbohydrate, doesn't matter what it is, every single one has this empirical formula. So 2 hydrogens for every 1 carbon and 1 oxygen that it has. Now there may be 8 million carbons in that sugar, but it's still going to have this empirical formula. So if there are 8 million carbons, how many hydrogens are there? 16 million. And how many oxygen? 8 million. Okay? 2 to 1. Okay? Always going to root back to that. That's helpful to know. Just because you haven't taken the quiz yet, it's helpful to know. If you've already taken the quiz, you're like, oh man, it's totally on there. Sorry. Surprise! If you haven't taken the quiz yet. So, many of these carbohydrates serve as energy molecules, right? This makes sense. Carbs are sugar. You're like, yeah, I eat a candy bar and I feel amazing for about 5 minutes and then I crash, right? That doesn't happen to you? I mean, maybe it's more than 5 minutes. Maybe it's an hour you feel amazing after eating a candy bar. Okay, so some carbohydrates are basically exclusively energy molecules. Glucose is one of these, fructose, and then we've got some others that they're exclusively energy. That's really all you can do with them is to break them down to free up energy. Now, many of these can be polymerized. So you can take glucose and you can string it together as basically an energy repository. You're like, I don't need this energy now, but I may an hour from now. And so you'll string it together. Plants string this together as starch. Animals string this together as glycogen. And so this is why, like when you cook a potato, it sweetens a little bit as you cook it, because you're taking something that's starch that your body doesn't recognize as sweet, and you're breaking it down into individual sugars, some of which your body will recognize as sweet. And you're like, potatoes aren't sweet. They are a little bit. But you take something like a plantain, that's probably a better example, very starchy when they're raw. But then as you break those down into individual sugars, they become sweeter. Or bananas as they ripen. Most fruit as they ripen. Early on, a lot of starch. And then as they ripen, they become sweeter as those sugars are released. Yeah?
Is that why when you chew something for a long time, it becomes sweeter when you crack over a piece of bread?
Yeah, because you're starting to actually access individual sugars that your taste buds recognize as sweet, rather than if you just swallow it and they're not broken down to those individual sugars until they're past your taste buds. Yeah, absolutely. All right. But some carbohydrates, so that's one of the reasons carbs are important. They provide energy. That's kind of important. I need energy. You need energy. Like right now, Dr. Engel, I could use a lot of energy. I do my best to talk really loud and to do weird things, make fun of myself, to keep you awake. I know it's hard. It's hard. I have a hard time staying awake while I teach as well. I recorded a lecture for my class the other day, and my wife was listening as I recorded it, and she's like, Matt, that was really boring. I was like, I'm sick. I can't. Anyways, sorry. So some carbohydrates serve structural roles. So they aren't just for energy. The cells are building things out of them. We see this in plants. Plants will string glucose together as cellulose, which makes up their cell walls. This is something we can't break down, which is why green plant material is so high in fiber. Basically what that means is you can't break it down and it just kind of works like a bulldozer through your intestinal tract. Which is really nice, right? That's why, anyways, if you're having trouble staying regular, right, you just increase the amount of fiber in your diet and you get that bulldozer just kind of moving through. Sorry, had to do it. I was thinking, should I do it? No, but yeah, actually, absolutely. But we can't break this down. There are some organisms that can. Like cattle, they have bacteria in their gut that can break down cellulose. And I don't know if you've ever watched a cow, but it'll swallow material and then sometimes you'll see material come up. And because it spent some time in the stomach, bacteria breaking down the cellulose, then it'll come back up, the cow will chew it more and it'll go to the next area of its stomach where it starts digesting. It's a lot easier to see in a giraffe because giraffes chew their cud as well like cattle, but the giraffe neck is super long. So if you go to a zoo and watch a giraffe, you'll see the material that it swallows go down, and then you'll see it come back up. It looks like a hotel with the elevator on the outside. You know what I'm talking about? When the elevator's on the outside, you can watch the people going up and down. It's like that. Another example of this is chitin. You find this in some animals and in a lot of fungi, where they string glucose together. There's some other stuff involved. They add some more functional groups to spice it up a little bit. But you can find, again, carbohydrates acting as structural elements as well. So why are carbohydrates important? What two roles do they play? Energy and structure. You're going to find that's a common theme. Energy and structure, although some things have some added functionality as well. So here are some carbohydrates, and again, here, this is where we're just kind of go through a lot of slides, but it's not a lot of information. Okay, these are what you might consider simple sugars. They're sugars that contain a single interesting functional group. You see that? One interesting functional group. One interesting functional group. One interesting functional group. So you're like, well, what about these? And it's like, yeah, those are, but when you've got this, we know this is far more chemically active than this, because the carbon here is sharing 4 electrons with an electron hog, versus these that are only sharing 2 electrons with an electron hog. Okay? So these have one really interesting functional group. Here's some information about what happens as these sugars actually form rings. So you take a linear form of the sugar and you actually wrap this around, because this carbon right here has a bond with 2 oxygen here. And so this carbon right here has a bond with 1 oxygen here. And so we can wrap this thing around and actually create something that is more stable, although it makes this carbon even more unhappy. Because now this carbon here has 1, oh no. So it's just as unhappy. It has 1, 2 bonds with an oxygen, right? And it had 1, 2 before, but now this carbon right here still has 1, which it did before. And so we haven't really changed the number of oxygen that any carbon has a bond with, but we've made something that's more stable. Because whenever you make a ring structure, this is something you don't have to remember for this class, but it'll help for you to understand why this happens. Whenever you make a ring, electrons can kind of float freely anywhere in that ring. And that's what electrons really like. They like options, right? Spend a little bit of time with this carbon, a little bit of time with this carbon, a lot of time with this oxygen because it's an electron hog, a little bit here. And so whenever you form a ring, the electrons can move around. And that makes something really stable. And so again, you don't need to remember that for this course, but it helps you to understand some things. Real quickly, as we look at this, we're taking 2 monosaccharides and we're stringing them together. What type of reaction is this? A dehydration or condensation reaction with water as a product. You see water is on the right side of the arrow. Okay, and we've taken these and we've formed a bond between the two. Okay, to take 2 monosaccharides and make them into a single disaccharide. Okay? Anyways, all right. So here we've done basically the same thing. We took 2 monosaccharides and we strung them together, but this bond's a little bit different. And so this sugar is a little bit different. It's called lactose. Are any of you lactose intolerant? Okay, and the reason why you're lactose intolerant is because you can't break this bond. And you're like, don't you just use water? Yes, and given water and enough time, it will break. But not before it's, wreaked havoc in your intestinal tract. Okay? So you need an enzyme and water to make it happen quickly enough that it doesn't just build up in your intestinal tract. Okay? And so the reason why you're lactose intolerant is because you lack an enzyme to break this down and you don't have bacteria in your gut that will break it down. So it just kind of accumulates. And when things accumulate in your intestines, they draw water out of the cells surrounding your intestines. And what happens when you draw water into your intestinal tract, if you can imagine? Now you don't have a bulldozer, you have a garden hose, right? So it's not the high fiber, it's just pumping water through it. It's not great, right? It's not a great situation. Which is why if you take like Lactaid, it is an enzyme that breaks down lactose. You take it before you eat ice cream because you're like, I'm not going to give up ice cream. I don't care how much my stomach hurts or how much I have to pay for these Lactaid pills because they're ridiculously expensive. You're like, I want to eat ice cream. So you take those like an hour before you eat your ice cream and you're mostly fine. Unless, of course, you eat like an entire gallon of ice cream. Oh, gosh, I'm just getting really off track today, but I got to do it. It's Friday. Have you ever watched like a competitive eating competition? And have you ever just wondered what they feel like after that's over? Because this is what I do. I watch the Nathan's hot dog eating contest every 4th of July. And they're up to now to win that competition, you have to eat like 70 hot dogs in is it 10 minutes or 12 minutes? I think it's 12 minutes. Anyways, you gotta eat like 70 hot dogs in 12 minutes. I'm like, what would you feel like? I ate 12 Dodger dogs one time during a single baseball game in the all-you-can-eat pavilion. I was pretty impressed with that. I felt awful. I just felt terrible. So I was, whenever you watch this, they show other competitions that these competitive eaters are involved in. And one time I was watching it and somebody up there, it said they won an ice cream eating competition by eating 2.5 gallons of ice cream in 15 minutes. 2.5, wow. Hopefully they're not lactose intolerant. All right. So here's a whole bunch of these strung together. What do we call that when we string a bunch of these together? Polymers or polymerization. They're strung together using what type of reactions? Dehydration or condensation reactions. And this is a starch. What plants will tend to store their glucose as. And again, it's just a way, let's store some energy for later. Okay? And then here's glycogen. Glycogen's kind of weird. You see these branches. So it doesn't form one long polymer like what you get in starch. You get this really branched structure. This is how animals store excess sugars. And really you store it in your liver. It's one of the main reasons your liver is so big. Right? Your liver also filters everything that you consume. But one of the reasons why it's so big is because it stores excess sugars. Because you need sugars in between meals, right? So you've got to be able to pull those from somewhere. Anyways, here's another polymer. We already talked about this one. This one's cellulose. This has a bond we can't break. No animal can break this bond. But there are bacteria that can break these bonds. And so there are animals that have those bacteria that live inside them. So porcupines, and I know this is a cell biology class, but it pertains. So porcupines, they don't chew their cud like cattle do, but instead they have a chamber at the end of their small intestine and the beginning of their large intestine called the cecum that's just packed full of bacteria that break down cellulose. All porcupines eat, really, is bark. That's pretty much all they eat. Now, a lot of like deer will only eat bark in the wintertime because there isn't anything else from the plant except for the bark in the wintertime. But porcupines, it's all they eat year round. Unless you put an orange out, they'll eat that. They love it. But so you can look inside their cecum. If you get like a road-killed porcupine, don't kill a porcupine, that's sad. But you get a road-killed one, you can look inside the cecum, and at the very beginning, you're just like, man, it looks like you scrape pieces of bark off a tree. Nothing's happened to it all the way through the small intestines until it got to that cecum. And then at the very end of the cecum, it's just soup. Because the bacteria have broken down the cellulose in that small amount of space, like 4 or 5 inches. It's pretty cool. It's pretty cool. Then you're like, I wonder what the soup would taste like. But you don't need it because it was road-killed and you don't know how long it's been dead. Yeah, Joe.
If you like ran over a porcupine, would it cost you fire?
Probably, probably so. It depends on what angle you ran it over at. But if you ran it over when it was walking away from you, very likely. Yeah. Those quills are impressive. I have another story. I'm going to share this with you. So, I went to school with a guy that was not very smart. And he was a fine student, but he made really horrible decisions. You know those kind of people, right? Okay, I am one of those people. So I went camping with this guy in the middle of wintertime. He lived in Montana, and I went camping with him. And just before I got there, maybe a week or two before I got there, his dog had been just demolished in the face by a porcupine. His dog went to bite a porcupine because his dog didn't make great decisions. And his dog's face was just full of quills, and it was horrible. Like, to have to pull those out of your dog, it's not a fun thing. So while I was camping with him, he found a porcupine. We were out camping, and he's like, there's no way this is the same porcupine, but I'm gonna take my aggression out on this porcupine. And I just kind of sat by, I'm like, whatever. And so he had a shotgun with him, and he decided he was going to shoot the porcupine from this far away with his shotgun. And I'll tell you what, those quills, when a porcupine gets hit with a shotgun shell, those quills fly a long distance. And so I stood back, and it had no problem making the 6-foot travel from the porcupine to his face. And it wasn't just like you tried to bite the porcupine so you get some of those quills. It was like, no, this porcupine exploded at his feet, and he got all of the quills. And it was all waist to the top of his face, just lit up with quills. And I thought it was awesome. So the cinnamon rolls was my best experience from the 4 years I lived in Ohio. This was undoubtedly my best experience from the 1 week camping in Montana with my buddy. And we're out in the middle of nowhere, and I'm a biology major. I'm like, dude, I got you. You know, I'm pre-med. I'll get those quills out. It took me 6 hours to get the quills out of his chest and his face. It was awesome. All right. Well, you know, it's 12:37. We've got 3 minutes left, but we don't have time to get through the next question. So we're going to pick up here on Monday. So what I'm going to do for Monday is I will retailor the quiz to be kind of a second quiz on chapter 3. Rather than going forward, we will undoubtedly get through chapter 3 on Monday. We're over halfway through slide-wise, and but it'll be another quiz on chapter 3. All right? Have a wonderful weekend. Happy Friday.